So if anyone was in the last session, Javier set myself up pretty nice with a description of coordinates. So I'm James Banting. I work at a company called Spark Geo. We're based in Canada, and we have an arm in the UK as well. And today I'm going to talk about discrete global grids and you. So I'm a remote sensing scientist, and this is not to scale, but most of my data looks like this. It's long strips that go from north to south or south to north, and this is what we have to deal with. So if you have a very long strip, you have to manage a lot of different projections and distortions, and you have to be aware of these because all these pixels will change over time. So what happens if I have a bunch of users that want a very wide area? In the last talk, we looked at Lambert conic conformal projections, LCC, where it maps very well east to west and west to east projections. So that's okay. I gotta support users that want this data, but my data is coming in a different capture mode. And what happens if I have a whole bunch of different users around the world that want very small areas? Do I use one worldwide system and just accept that I have distortions everywhere? Or do I drop down to local coordinate systems and have to map from one datum to a bunch of different projections every single time? So there's a couple different ways you can approach this. I like DGGS, Discrete Global Grids. So when we're thinking about this, it's good to go back to the basics. Aristotle and Plato have very good arguments on this. So Aristotle, his argument was like, represent the Earth as it is. Represent objects as they are. Don't try to simplify them. Plato, on the other hand, said, why don't you just simplify everything and make life easier? Tackle the easy problems first. So he came up with the Platonic solids. So this kind of forms the base for discrete global grids. Depending on how you put these together, you can put multiple together if you want, or you can just use one and explode them. You can start describing some pretty good objects. So in the real world, we have datums, we have projections. We use something called, in North America anyway, NAD 83 and NAD 27, and then we have the World Geographic, I think it's World Geographic System from 1984. And this represents the Earth as it was in 1984, or 83, or 27. In Canada, the energy companies there like to store all their data in NAD 27. And this presents a problem when you go and try and find an oil well, for example, and it is moved 100 meters because plate tectonics, the Earth shifts. So you have to account for all of this. You can look at things like MGRS, the Military Grid Reference System. And this is what Sentinel-2 satellite data is aligned to. Military Grid Reference System was designed to accurately land artillery shells. It was made by the US military for that specific purpose. So they want to know and be able to quickly calculate where their artillery shells are going to land. Web Mercator makes it very easy to look at geographic data on a web map on a 2D screen, usually a phone or a computer. But then you get this ideal world, this metaverse that's coming out, and you get map projections. You get things like Universal Transverse Mercator. And these are designed to push distortions to the edge. You want to create a projection for your area of interest, and then everything else is, I don't really care about that. It's not my problem. It's someone else's. Google came up with their S2 grid, which is a Hilbert curve on a cube. Uber has one called H3, bought Foursquare, which also uses H3. These are discrete global grids idealizing the world, trying to make it an easy problem to solve. Someone I like is Buckminster Fuller. Buckyballs, if you're familiar with that term from the carbon-60 atom. His whole goal was to discretize the sphere. So he came up with this Dymaxion map projection, and his goal was to not split up any land surfaces. So he created this projection so that the land is continuous all the way through. Water he wasn't concerned about, but he just wanted to make a very nice projection. This is probably my favorite projection to look at. It's wild, it's goofy. So when we're thinking about map projections, you have this real world object let's say a country, an area of interest, and you reference it to some sort of spheroid. So you do a reference on a datum. And from that datum, you need to take it to a map. You have to project it out. And you need to preserve some sort of distortion. Usually it's distance, it's direction, it's shape, or its area. EPSG 3857, which is Web Mercator, preserves shape on there. So that's the one that that we all are familiar with. Mirroring kind of the geometry and the geography world, you get something called geodesy, which is where discrete global grid systems fall under. So as I mentioned, you have Web Mercator, which is the same as EPSG 3857. Some people call this Google Web Map. There's also a EPSG 900913, and if you write it out, it spells Google. It's kind of goofy. I like it. But these are all different map projections for specific use cases. Again, MGRS is there because it's the one that covers the world. It's based on UTM projections, and it has the 60 grids and then the 2 UPS grids for the poles. And it solves its need, but when you get down to the intricacies of discreteness, you want to make sure that an area on the Earth is the same all the way, or an area on the Earth is the same ID every time. MGRS kind of fails. So we have something called Discrete Global Grid. So this is a gridding system which each cell is unique at a given resolution and projection. So you have this map scale that sits there, and that is Discrete Global Grid. The system comes in later on, but a Discrete Global Grid has no overlaps and it has no slivers. So each location can only be defined by one ID, and there's no locations that are left out. It operates in 3 dimensions, so X, Y, and Z, and the goal, again, is to discretize the sphere. So we add a system onto this. So we create a whole bunch of different grids together, and we make them hierarchical. And you get some really smart mathematicians in there to make sure that it has geometric properties of alignment, adjacency, congruency. So this means that each cell has a parent that you can reference, and it has children that you can reference as well. And if you know the ID of one cell, you know the neighbors all the way around. So given an ID, it's unique. You can traverse up and down and X, Y, and Z. DGGS are interoperable as well. Because it's a projection system, if you want it to be, you can move between different discrete global grids. So you can go between S2 and Uber H3 if you need. There's a little bit of distortion properties that happen there, but as long as they're known, you can account for them. So this is one H3 for Uber and Foursquare. One thing you'll notice here is it's not square. We're using hexagons and pentagons as well. Just the way that hexagons wrap the Earth, there's not enough space, so you have to throw in a pentagon there. And these are really good for movement analysis because instead of 4 sides that data can flow, you suddenly have 6 sides or 5 sides that data can flow. So Uber really likes this because they are moving cars around. This is great for other applications like watershed management as well, because water doesn't flow in north, south, west, east projections. So H3 is really good for movement analysis, but it gets kind of annoying when you want to map satellite imagery onto it, because satellites usually capture things in pixels, which are square-ish. There's another one called RealPix. So this is made by NASA, the Jet Propulsion Laboratory, and it was originally created to look outward. So they wanted to map the cosmic background radiation. So instead of, Z was essentially time that they're mapping. If you invert this and put it on the Earth, it creates a nice discrete global grid to map locations. It gets kind of funky at the poles. As you'll notice, we have triangles up at the top and at the bottom, but for the most part, the data in the middle of the Earth is going to be squares. And you can go up and down them, you can go across, you know where you're going to be at every single time, and each of those cells has a unique ID. Another one is called Ease Grid, and this is built by the National Snow and Ice Data Center in the US. And it's very popular for remote sensing data because it has a projection system built into EPSG. So you can jump through this and map your data effectively out and in, which makes it a very, very approachable for remote sensing people like me. I was talking with Jérôme from Écrit, and he has been working quite heavily on this discrete global grid. It's called the, ixoctahedron Snyder equal area 9 aperture rhombic. And an aperture just means that it's the number of children underneath that cell. So there's 9 children under there if you split it up. You can have different apertures. You can have 3, you can have 4. You just need to make sure that it's a square. So this is right off the press. Jérôme has submitted things to OGC for this. What I find really interesting about this one is that it mixes the pentagons and the hexagons with squares. Sort of squares, rhombus. So what you can see is you can get movement data at different levels, and then if you put triangles together, you get a rhombus, which you just need to distort into a square grid. So it makes it very, very accessible for vector data as well as raster data. You get a global grid that you know the unique location. One of the things you have to consider, though, is the line bisects some of the hexagons. So you just need to be smart about how you manage your data. I'm very excited to see where this goes. Right now, there is a projection, but it only goes one way. So you can go out, but if you have your data, you can't go back in. One of the cool things about this as well is that it aligns, it's axis aligned, so it aligns to latitude and longitude coordinates. So you can jump your data wherever you need to. Okay, I want to get into military grid reference systems, and this is the reference system that most people are familiar with that covers the entire world. As I mentioned, Sentinel-2 is aligned to this, so if you've downloaded Sentinel-2 tiles and there's just one sliver, blame MGRS. It's made, as I mentioned, for landing artillery shells, but it works pretty good for not killing people. You have an increasing precision, so you have a grid zone designator that's built with angles, and then you go down into like a meter system. So you have 100 square kilometer, and then within that you have 10 meter. Within that you go down to like 1 kilometer. So it increases precision, and you have a unique location most of the time. So this is what a grid looks like. This is the United States. So these blue lines are the grid zone designations, and it's 6 degrees by 8 degrees most of the time. So it's good for like identifying states and country level information. If we go further down, I've thrown up kind of a generic satellite strip here, 20 kilometers by 5 kilometers, just to give a sense of scale. So these are the 100-kilometer grid squares. What you'll notice is it doesn't align very well. So if you have the grids here, they don't align precisely with those grid zone designation identifiers. You have to drop down and recreate your grid. Further on to that, we have the 10-kilometer level. And again, I've thrown the generic satellite strip on there. And this is what it's going to cover. Again, it doesn't align, but you get more information. You can start having unique locations that you can point at. And then down to the 1 kilometer level. This is great for small neighborhoods and smaller geographic features. And you get a lot of data clipped into there. So this is where the Sentinel-2 strips come from. It's MGRS, and it's annoying. One of the things that MGRS, so it's been described as a discrete global grid, but it is not unique. So where you have 2 different zones come together, you'll try to have your distortions pushed to the edge there, but when you come to align the grids, you can deliver data in 2 different projections, and it's still valid. So these are not discrete. Like I have 2 locations that have, or 1 location that has 2 unique IDs. This is in violation of the discrete part of discrete global grids. So what we did was we wrote some code and grabbed other people's code, as one does, and looked at the DGGS level as well as the cell size contained within these levels. And we turned into a log graph. But what I wanted to highlight here was where these lines line up. So this is where we get interoperability between the grid systems. So for example, MGRS in purple here, you can see where it goes down 1 kilometer, 10 kilometers, 100 kilometers. It changes, it does not change here, but there is another one, this EASE DGGS has different apertures as you go up and down. So 9 children, 3 children, 6 children. And you can see where it changes. So it comes down here. It aligns with MGRS very well at the 1 kilometer level and follows it all the way down. S2 from Google, for example, just has a pretty straight line all the way down, but it doesn't really align with anything exactly. You can get close, but not exact. H3, for example, you can get close, but not exact. So if you get data from H3 or S2 and you want to put it into a different projection system, this is where you need to do that projection. Get your resolution your data at a certain resolution, and then you can jump across with minimal distortions. There's one here called Equi7, which goes up to the right, and that's not a bug. Equi7 is a discrete global grid that is 7 grids. It's not discrete because it overlaps 3 grids in Spain, but it's intended to not break up land masses. So you pick your land mass and you have your discrete global grid for that specific landmass. Again, it's not discrete because you can have multiple IDs represent the same location. That's it for me. I hope you enjoyed this presentation.